atoms on a surface, and we measure it with a scanning tunnel microscope. And this work has been done in the group of Andreas Heinrich at IBM Almaden in San Jose. My lab is always also affiliated with the University of Basel to get my degree. Now, spin resonance is a tool that's actually used in many fields and is indispensable in many ways. The most famous example is probably an MRI, where it's not electron spin resonance, but nuclear spin resonance. And we can take images of, for example, tissue or other things, and we do that by a pulsed magnetic field, at least in an MRI. And then, basically, what happens is the proton, or the nucleus of the hydrogen atom, is manipulated on the Bloch sphere. And with some pulse sequences, one can distinguish between different tissues, refocus those signals that come out, detect it with some detection coils, and actually produce images. Here, for example, Humer's brain. Now, a technique like this uses a very large amount or ensemble of identical spins. In nuclear spins, this is typically about 10 to the 15 nuclear, 10 to the 12 nuclear spins that you use to get a good signal. And for electron spin resonance, it's about 10 to the 7 electrons that you need. Now, today I want to show you something where you can do it on a single spin. But we're not the only ones that do that. There's other techniques, and for example, a lot of the qubit measurements are also spin resonance measurements. Now, one example that uses small ensembles of spin is, for example, magnetic resonance force microscopy, which works very similarly to the MRI, just on a miniature scale and with scanning capabilities. Another example are ND centers in diamond, where the spins are optically read out and manipulated. And a further example are donors in silicon, for example, phosphorus, that are read out electrically. And I'd like to add now basically these atoms on a surface read out with a scanning tunneling microscope to this. So let's have a look at the system that we're studying. We're using iron atoms on magnesium oxide. We have thin films of magnesium oxide. In fact, we have 2 monolayers of this thin insulating film. And we use this because we need to decouple our atom from the metallic substrate. In our case, the metallic substrate is silver. Here is an image of our substrate, how it looks like, or the sample, how it looks like typically. There is these patches of magnesium oxide. For example, here I labeled it, this is a 3 monolayer thick MgO layer. And up here is a 2 monolayer thick or 4 monolayer. So we can vary the thickness a little bit of this substrate. And also there's areas of bare silver in this. The iron atom sits on top of the oxygen atom and basically surrounded by 4 magnesium atoms and this 1 oxygen atom underneath. So it is basically in a 4-fold symmetric surface or environment that it is living in. Now, if we talk about atoms on a surface, they're basically like tiny atoms, tiny magnets. Now, to characterize magnets, one property is the magnetic moment mu, which is the strength of the magnetic moment, or the magnet, and then there is the magnetic anisotropy, which basically is a preferred axis that the spin or the magnet wants to point in. And to flip between the different magnetic orientations, there's usually an energy barrier that you have to overcome. And basically to flip from one orientation to the other. Now, of course, when we are talking about these small structures, there's not a continuous barrier that you have to overcome, but more likely it's something that's quantum mechanics, and it has levels. So I want to describe this with a spin Hamiltonian. And since iron is an atom with 6 electrons on a surface, it has the orbital moment, according to Hund's rules, of 2 and a spin moment of 2. So what that, the consequence of that is that you have 5 concrete levels in your energy diagram for the iron atom. And you can describe it with this very simplified spin Hamiltonian of an anisotropy term and the spin operator in the out-of-plane direction. And basically, we could label now the lowest energy states in our systems are the plus and minus 2 spin, spin in the z direction. Now, to learn more about the system, we do scanning tunneling microscopy and, in fact, actually spectroscopy. So we have a metallic tip, we have our magnetic atom, our insulating film, the MgO, and again a metallic substrate, and then we measure conductance through this, and basically read that out. So here we have conductance versus the bias that we apply, and as we increase the bias, as long as there's no excitation in the atom, nothing happens and the conductance stays constant. But once the bias is large enough that rather than just tunneling through the barrier, you can also excite something in the atom. There's basically, what happens, there's a second conductance channel that opens up, which manifests itself as a step in the conductance spectrum. So these are excitations that you can see as steps in the conductance. In our case, these are spin excitations, but of course you could also see vibrational excitations. Now, in a real system, in our iron atom on the surface, this spectrum actually really sort of looks like that. It's not entirely flat, but there's a clear step, and in this case, it's at 14 millivolts. Now, this step that we see, these 14 millivolts, this is the excitation from one of the ground states into the excited states, here labeled as 2 and 3. So with this, we basically now know more about the spin Hamiltonian. In fact, we can write down an actual number for the anisotropy. And in a magnetic field, when we apply a magnetic field, we can also split up those levels, and this is just the Baumann term. In our system, when we put iron on the surface, this is not just a spin actually, but there's also a large orbital contribution to this. And that gives it a large, basically G factor that's 2.6 rather than the typical 2 for a spin. And this basically just shows how large the magnetic moment of this system on the surface is. In this simplified model, it just comes into this number of a large G factor. Now, from now on, I want to focus on just the lowest 2 states, the state 0 and the state 1, where we want to drive ESR transitions between those 2 states, and basically use these as our qubit. Now, how do we do this? We use our STM setup, and we apply an electric field, an oscillating electric field in the junction to actually drive this transition. And basically this RF is just added to our normal DC in our normal voltage in the junction. Now, what we want to detect is basically a change of the population. So when we start with it, the atom is in the ground state, is only thermally populated, and what we want to do is we want to drive it with the electric field so that it's randomized and it's actually driven to 50% of the excited state. And that happens at a certain center frequency, the resonance frequency. Now, we can't read out the population of the state, but we can read out current and translate this into the population. Now, why does this work? this is basically because we use spin polarized tunneling. What we do is we take individual iron atoms and transfer them to our tip, so to make our tip magnetic. And then we have this spin polarized tunneling, and that's basically an atomic scale tunneling magnetoresistance junctions. So here I have an example of this, just to visualize it a little bit. This is an array of 8 iron atoms that are antiferromagnetically coupled. And when my tip is aligned with the atom on the surface, this gives us a high current signal, and the atom appears tall. Now if I move my tip over to the next atom that's now anti-aligned with the tip, the current is lower, and the atom appears short. And so in topography, all of these atoms are actually the same height. But when we take in the magnetic signal, they appear as different heights. So like this, we can distinguish between what state our atom is in. Is it aligned or anti-aligned with our tip? And now all that's left to do is actually look at one single atom and try to drive it with this electric field, with this oscillating electric field. In contrast to most conventional ESR experiments, we sweep the frequency between 20 and 30 gigahertz. Most experiments sweep the magnetic field. Now, and what we do is we have the static voltage that we apply, and then the oscillating on top of that. And this is how a trace like that looks like, where we have a clear spike around 23 gigahertz at this magnetic field. Now, to show that this is really the signal from a transition that we can drive, we can just change the magnetic field, and as we change the magnetic field, the splitting should become larger, and this peak should move. It's in frequency then. Now, I want to point out really quickly that the signal is really small. It's only 50 femtoamps, so it's a little bit of a challenge to actually also detect it. Now, how does this work? How can we drive spins with an electric field? For that, we have to look again at the immediate environment of our iron atom. The iron atom has, as I said before, the oxygen atom and the 4 magnesium atoms around it. And what happens, electric fields don't basically manipulate the spin directly, but what they do, they manipulate orbital moments. And basically, they move charges around. And so what happens is that because the iron has an orbital moment of 2, it matches the 4-fold symmetry of our surface. And so that means that we can actually change the ligand field, which changes the anisotropy, and that allows us to coherently transition between these states 0 and 1. And now I want to look a little bit more on the spin resonance parameters that we have. For example, here is one peak that we zoom in that's at a center frequency of 25.7 gigahertz. And basically, when we have a low drive amplitude, then this is a limit on the T2 time. The T2 time is the dephasing time of the spin rotating. Now, in our case, this is actually usually driven a little bit more than the limit, or than a good driving. So this is a lower bound. If we take the full width at half maximum, this is basically a lower bound on our T2, which is around 100 nanoseconds. From other experiments, which I don't have the time to go into, but we can do also measurements of T1, basically the time from the system when it is in the excited state 1 to relax back into state 0. This is from a pump probe experiment. And there we know that the T2 is around 10 milliseconds in this case. And now, finally, what we can also do is we vary the drive amplitude and basically figure out a more precise T2 parameter and also the Rabi rate of our system. And the Rabi flap time is about 1 microsecond, which is of course not optimal because our T2 time is only 200 nanoseconds. Now, I'm saying only because yesterday we had some talks where it was 2 seconds, and it's a lot more than what we have. But you have to bear in mind that this is still on a conductor, and this is the first experiment. There's lots of ways to improve this. For example, go to thicker insulators and all these sort of things. So lots to do with this. Now, what I also want to show is that this, of course, doesn't just work on one atom. Now, we have the tendency to name our atoms. The one that we worked on so far is called Beatrix. And we have a whole bunch of others, Chris, Earl, Fred, and George. And what I want to show here is that they have some little changes in the neighborhood. So what it affects is basically that the frequency the resonance occurs changes due to these small changes in the environment. Now, this basically, the difference between these lines would in conventional ESR come up as a line broadening, because you would take the average over all of these different atoms. Now here we can go to 1 and like that have a very good resolution. And it also actually improves the energy resolution of the STM tremendously. Before, the spectroscopy that I showed you basically is limited by temperature of the system. Now with this, even at the same temperature, we can get to a much, much better resolution. In fact, about 10,000 times better than what the conventional atomic spectroscopy had. Now, you might notice that there is some sort of a scheme in here. A is missing because Andy died, and then there is Daisy missing. Daisy is this atom that's next to an atom that I falsely colored in green, and the green atoms are not iron atoms, but they're cobalt atoms. So let's take a look at Daisy a little bit closer. So these two atoms, the iron atom and the cobalt atom, are very close together. And what happens if you have this? Basically, the cobalt atom has a magnetic moment too, and when it's in its ground state, when it's in its ground state, it reduces the local magnetic moment of the iron atom, and therefore it shifts the frequency a little bit down. And of course, if the cobalt flips and is in its excited state, it moves it a little bit up. So we basically get a splitting of the frequency that we see due to the neighboring atom, even though we only look at the iron atom. And this is just for playing, this is kind of something that for qubits would be really nice, because this is already sort of a conventional conditional NOT gate. You can operate on the iron atom with the condition that your cobalt atom has to be in a certain state. Of course, for this, there's still a lot of development that has to be done. For example, you need longer T2 to actually be able to do operations. And you also need pulse ESR, but it's just a kind of way of looking at what could be done with this. And other things that can be done with this is actually use this splitting of the ESR, which I plot here, for sensing. And basically, when atoms are far apart, the splitting between these two frequencies is very small, and then when they're close together, it gets larger and larger. So this is dipole-dipole interaction. And with that, we can actually determine magnetic moments of close-by atoms. So for example, when we have our iron atom to probe, when we have an iron atom next to it, that's what I just showed you. And then with cobalt next to it, it will have a different curve. And then there is something that we call the big iron, which is maybe a different charge state of the iron. We're actually not entirely sure what it is. But we can, with this, determine very precisely the magnetic moments of these nearby species, even though theory might not actually be as precise as that. With this, we can actually really be a lot more accurate. And then we can go ahead and use other capabilities of STM to play even more with this. For example, here, Taeyong built this really nice structure of just arranging 5 atoms, and I'm probing the center atom. which gives a really nice ESR spectrum, where the first peak is when all the neighboring atoms are in their ground state. Now the second peak arises because one of the 4 atoms around it isn't now in an excited state. And then of course the next peak is if 2 atoms are in an excited state. And you can go a lot further than that. You can now push this atom somewhere else, and then the peak with the 1 excited state splits up into many other peaks, and all degeneracies are broken. So basically, this gives a lot of a playground to do things with. And you could, of course, once you understand this, also turn around and say, well, if I probe 3 corner atoms, can I exactly determine where our other atoms are? And you can do that. You can precisely locate other atoms, or you could locate maybe magnetic moments in a molecule and so on, just by using this kind of atom manipulation together with this ESR. And with that, I'm already at the end. I could also give you a lot more details on why this exactly works, or how we do this technique, whatever you'd like. But first I want to thank Andreas, the principal investigator, and William and Tae Young, the 2 great postdocs that I could work with, and then Chris and Bruce are permanent at IBM that are also crucial, and Arjun was actually the ESR expert that helped us a lot with understanding this. Thank you.
Lots of time for questions. So questions. Please.
So if you put your 2 irons or iron and cobalt atoms very close, then the magnetic interaction may be stronger than the crystal field interaction. Then, for example, in that scene, with the magnetism of the iron, you see like a dimer, and not magnetic dimer of the state.
That's true. If you, sorry. Here is already some indication that when you go closer, that there's not just dipole-dipole interaction that comes into play, actually, yes. From conventional spectroscopy, the atoms still act pretty much as iron atoms, even if they are very close. They do interact, but not that they become something very different. They need to be really, really close to actually become a dimer in this case. And that's also just when we move them, we can play around.
And the computing energy scale is the crystal field, I mean the anisotropy.
Yes, yes.
So I was going to ask the question about the mechanism. Should I think of this as a manipulation of the G tensor? And is that the way in which you're converting the electric field into effective magnetic fields?
Basically, yeah. I'm not sure if I'm exactly clear on what a G tensor is. Basically, this would be the energy spectrum of this, which now, this is a little bit far out, but these are basically the atomic multiplets. So here is really, according to Hund's rule, L equals 5, S equals 5, so that's a 5D, and they split up due to the ligand field, right? The axial and the cubic, these are the ligand field contributions. And then what we basically do is we wiggle these two, between those 2 states, and that then we can zoom in into that. Basically, here. Oh. So basically now these are the zoom-ins, and we wiggle the ligand field between those, and that affects now the lower state, so that the mixing between these is different, and that's why we can do the manipulation. Should I go a little bit slower? I can start this again.
No, but I think that will give you one type of interaction. Changing the magnitude of the heat factor is, I think something insufficient to drive transition. You need to have something that changes the direction. You need an effective transverse magnetic field.
Well, the field is on an angle because of because of a different experimental issue. But basically, what drives the difference? Well, I guess it is the angle, because we do use this angle to actually get some more mixing between the spin states, and that will in the end allow not just to change the G factor, but actually have some overlap of the wave functions that gives us this possibility to do the transitions. So yeah, we have this field that we do in plane just because, yeah, we want to have some more mixing. Basically, I have the wave function somewhere. So if we had just an out-of-plane field, the states would be ML, MS plus 2 and plus 2 plus 2 and minus 2 very clearly, and the spin is very polarized, a very small contribution. And so the problem is that when we then have this Hamiltonian, the time-dependent Hamiltonian that basically causes these transitions, the one that we use in a simplified way is L plus to the fourth and L minus to the fourth. And so what is the problem if we just have a VC field? Then that doesn't really do anything, because we can do this, but we can't go between those because the spins are still polarized. And so that's why we apply an in-plane field to mix those, and then we actually get an overlap that can do it.
Related to the same question, but I was going to ask whether either cobalt spin or discrete events where it flips from one configuration to the other, or is it always precessing?
In the cobalt, basically. So because you mean with the two?
Yeah, because you see two peaks. Does it switch back and forth?
So this measurement is not fast enough that we could do this, but we can change the size of the two peaks with temperature. So the cobalt actually has a lifetime of 200 microseconds in an ideal case, so it's too fast for this.
So maybe I have a quick question. So you said in order to increase the T2 time, you could think about maybe making the MGO thicker to decouple it from the silver underneath, yeah. But then STM gets hard, I guess.
Yes.
Is that so? I
It does.
There are ways that you can think of, making this a cleaner system.
Yes, there are other ways. Of course, there's always the possibility to think of other systems, or for example, maybe do something with a molecule, try to shield your atom more in the same symmetry, but shield it from the metallic substrate more by putting it in a molecule, for example. But yeah, so there's a bunch of things that one could think of, but all needs a little bit of development.
Any other questions, please?
Yeah, so this is a very different question. Sorry, some kind of open-ended.
Anything's fine.
But rather than just looking at single spins, suppose I've got a surface where I know, or I expect there may be fluctuating magnetic excitations. Is it possible to do reliable spectroscopy of those excitations? I'm not thinking about NMR or ESR. I'm just thinking about looking for the spin waves, if you like, spin transitions. And has that been done?
So you mean with exciting those?
I just
also?
excite spin waves, magnetic excitations, localized things, and get
So
the spectrum of those excitations by taking a derivative spectroscopy in STM. As you said, it's just an inelastic process of some kind.
yeah, so there's definitely different efforts, and what's one thing is that if you do STM and you want it in a spatial thing, it's usually pretty slow. It's not a fast scanning mechanism. So you would need something where you could locally stay at one place and then do something like pump probe, and then you can do certain things. And there's efforts of people trying to excite things like that, or also charge waves with light and then probe that and all that. But I'm not sure of all the details with what you can do. I mean, definitely there is, with this pump probe technique, that you can excite and measure repeatedly, you can definitely get dynamics really fast of systems.
You mentioned something about some defects in one of those plots, those small black dots.
Yeah. We're not sure. There might be something that's underneath. It's not something that's really a defect that you see very well on the surface, but it's just a little bit of a.
Did you try probing them?
Not really, actually. Yeah, we tried to probe some of the edge defects because some of the oxygen vacancies should be ESR active too, actually, but usually we don't. Yeah, I mean, these defects, they could be somewhere deeper down in the surface too, and so we didn't spend too much time on that.
When you showed the Zeeman shift of the line for a single iron atom, it looked like the line shape was changing with field. Is that right? And if so, how well understood?
Oh, yeah. So you mean that it has a little bit of a funny shape, our spectrum?
Right, it looks like it's the phase is changing as the field increases or something.
Yeah, I mean, they definitely have a little bit of an asymmetric shape, which I'm not an ESR expert yet, but I'm told that that's actually because of the conduction electrons of our silver underneath that kind of makes it asymmetric. And I'm not sure how that influences the magnetic field, so I'm not sure, but yeah.
Actually, maybe I have a related question. So when you have the coupled cobalt and iron dot, and then you were showing as a function of whether they're parallel or anti-parallel, you can shift. Those line widths are the same or different? And they look like they might be different, but then it wasn't obvious to me why they should be different.
That's a good question. I'm actually not sure of the answer if they are
So the
different. Yeah. I'm not sure. I haven't really looked into the different line shapes.